Hey, so effectively, what that entire problem you're given comes down to is solve that integral, right? It wants you to solve that integral somehow, right? And as it turns out, that's impossible. You actually can't solve that normally. It can't be represented as what's called a elementary function. It's not really important what that means. Basically, it just means you can't use any normal method. You can't use integration by parts. You can't use powers of sine cosine. You can't use trig sub. You can't use any of that stuff. Any of the integration methods you're given in class or taught to know how to use won't work with that, right? And it's been proven that you can't use those methods. So what are you supposed to do? Well, as it turns out, you can actually, if you can remove some of this weird stuff right here, the -1 and the squared, you're just left with e to the x, right? And so they're kind of similar, right? E to the x, -x squared is pretty similar to e to the x. So if we can do something with e to the x, which we know how to integrate, we know how to deal with, and we know a lot about e to the x, we don't know a lot about that. So it turns out what you can do is represent this e to the x as a Taylor series. Now, that is the general form of a Taylor series. And the reason why we want to get e to the x into a Taylor series is because we can actually integrate these series. Now, for this specific instance, c is what's called the center, right? And for e to the -x squared, for what we're going to use, we're actually going to set the center equal to 0. All right, so it's x minus 0 to the k, and that's what's called a Maclaurin series. But these two things are effectively the same thing. It just means that the center is 0 for a Maclaurin series. So we're going to use a Maclaurin series to try and solve that integral. And because that integral is hard, and we have to approximate it to get an answer. So, like I said, we can actually integrate series pretty easily. Right? Here's a quick example right here. The c actually goes out in front. There's a couple instances where you have to do something special with it, but that's effectively what you have to do. K is going to be a constant at any point, so the k plus 1 stuff, this is just a normal power rule, right? This answer is a normal power rule. So that's just an example of integrating a power series, and that's actually what we're going to do, very similar to that. We're going to use something very similar to that and integrate that to try and solve that. So what does that form mean, right? How can we get e to the x to fit that? Because I should be able to represent e to the x in a Maclaurin series, but there's a lot of weird stuff that you have to do, right? So that's what these steps are. We're going to translate e to the x into a Maclaurin series because we want to integrate that Maclaurin series to make our problem easier to do. Right, so that f to the nth of 0, that means it's the nth derivative, right? It basically just means you take the derivative an infinite number of times and then you plug in 0 to what that answer is, right? So our original function is e to the x, the first derivative of e to the x is e to the x, the second derivative is e to the x, the third derivative is e to the x, blah, 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 it goes on forever, right? No matter how many times you take the derivative of e to the x, it's always going to be e to the x. So if we punch in 0 to e to the x an infinite number of times, you're just going to get 1, right? Anything to the 0 power is 1. Not anything, but almost everything to the 0 power is 1. So the fact that it's 1, we can replace the entire numerator with 1, right? So you're left with 1 over k factorial x to the k. But we actually have to see what happens to those things in a series. You have to sort of expand. You have to sort of punch those numbers into the numerator and then sort of expand it as it goes to infinity. And what effectively happens is you put a 1 here, a 1 here, 1 here, so the 1 stays forever, and you get a 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, it goes on forever. And same with the powers here, right? So what we do is we represent these changing numbers here. We represent these changing numbers here, the factorials and the x's with k, right? because you want to get this long series into like a closed form, a really nice like thing that you can deal with, right? Because no one wants to write that out forever, right? Because these things, because we're trying to get that into something like that, but the nth derivative at 0 is not something that we want to work with. We want to work with something that is sort of a direct approximation of e to the x, because we want to approximate any term for e to the x with a series, because that's what the series does, right? So if I want to know what e to the third power is, we would use a series right here to get an exact approximation of it, right? So if you replace all the changing numbers with k, you replace all the factorial numbers with k, you end up getting that 1 over k factorial x to the k, and the series, it goes from 0 to infinity. That's e to the x. You should memorize that. That's a useful formula that you should memorize because it's used quite a lot. Now it's important to notice, what you might have noticed is that why don't we just plug in 1 to the top there and just leave the k and the x to the k, right? I mean, why go through all this stuff right here trying to see where the k's fit, trying to get into a closed form? Why should I do that? Why can't I just plug in 1 up there, plug whatever these derivatives are into there, and just put it in that form? Well, you have to go through those steps. You have to go through those steps because e to the x is a very special example. Because e to the x is very special because if you take the derivative an infinite number of times, you get the same thing, right? So if you use this for other functions, say sine of x or cosine of x, you actually get something different. This is the power series for sine of x. You get weird stuff. Weird stuff happens. So you should follow these steps right here to see what the pattern is and get it into a form that makes sense. Because you don't want it in this form, you want it in that form. Something, it's called a closed form. It's very nice. Okay, so why don't we just go back to the original problem then, right? We're asked to integrate that, and we can't really do that, but we can integrate e to the x, right? We can integrate that. That's what this thing was over here, right? We can integrate that. That's actually really easy to integrate. It's just a normal power rule. So if we just plug in the negative x squared into e to the x, right? Because these, see the similarities between these two right here? We can actually plug in e to the x here. You plug in what that x value is and just plug in that negative x squared. So these two things, this and this, are exactly the same, right? So if we simplify that a little bit, because we're trying to integrate this whole thing from 0 to 1. So if we simplify it a little bit, we can actually pull the 1 out like that, and then bring the 2 up to the power, because power to a power you multiply, and you get x to the 2k, negative 1 to the k over k factorial, evaluated from 0 to 1 dx, right? Now, we're taking the derivative with respect to x, which means k is treated as a constant. So when we integrate that, it ends up becoming that. And because it's just 2k plus 1 over 2k plus 1, and you just move it over. And negative 1 to the k, I pulled that out from here. So I just did negative 1 to the k, and I just ka-chunk, pulled it out. And negative 1 to the k is really important. Use that for a lot. Notice how these two are very similar to one another. They're really similar, actually. And it's partly because of what this is. Negative 1 to the k alternates the series. It changes the sign from negative 1 to 1, negative 1 to 1, negative 1 to 1. Okay, so this is effectively our answer, right? This is the answer, but we need to sort of simplify it, and we need to evaluate it from 0 to 1. And we do that normally, right? Since we took the integral with respect to x, we just punch in 1 to x, and we punch in 2 to the x, and we subtract them from one another, right? So that's what this is, right? You just punch in 1 to the x, and you punch in 0 to the x, and then these are two different series, and we subtract them from one another, right? Well, anything, if you 0 is in the numerator, remember I just moved it out, but anything times 0 is just 0, right? So that whole thing goes away. That whole thing just goes to 0. And 1 raised to any power, right, because this doesn't go backwards. This starts at 0 and goes to 1 in the positive direction. It doesn't go the other direction. So we can get rid of that 1, right? So that thing goes away, and we're left with that. right? And that's your answer, right? This is your answer right here. Negative 1 to the k over k factorial 2k plus 1 equals the integral of e to the negative x squared dx evaluated from 0 to 1, right? And that's your function, right? So that's how you solve an integral like this. You use a Taylor series to try and approximate what e to the x is, and then you sort of punch in the other weird stuff, right? So this could be like 30x squared or 25x squared, and you plug it in like normal, right? Because this is where we plug it in here. We just plug in whatever's associated with the x into the power series for e to the x, which is that thing. So like I said, you should memorize that. This is really useful. There's another one for sine and another one for cosine, although you don't really need that, but you should memorize that. Okay, well, your problem also wanted you to get sort of the 6 terms of f of x, the 6 numbers of f of x, and that's effectively just 6 terms of the series. I wrote those out right there. That's effectively just the first 6 terms of that series, and that's just if you just punch in the numbers from 0, 1, 2, 3, 4, 5, that's what those are. So if you just evaluate that series 6 times, or if you just punch a number 6 times in that series, you'll get that, and those are the 6 terms of the series, right? And that's what that is. It wanted your w sub j and x sub j from 1 to 3. It wanted 6 terms of f of x, which is what that is, but it also wanted the first 3 terms of w sub j and x sub j, and they just mean the first 3 terms of this series. So just that, effectively. So that's your answer. Power series are really useful because they allow you to do stuff like this, allow you to evaluate weird integrals. And he just used a very weird notation. Never saw that before. So normally I deal with this notation right here, geometric, AR to the k, power series bk, x minus c to the k. Those can be represented from what he was using. Your professor was using w sub j and x sub j, but those can be represented right here, and that's what that is right there. So your w sub j is the AR to the k, and the x sub j is x minus c to the k. This is a more common notation. He used a really weird notation, which is why it was confusing, and it took me a while to even understand what he was asking, but that's what this is basically. AR to the k is your w sub j, and x minus c to the k is your x sub j. And this can actually be simplified. Your c is 0 at this point. Now, you may think that you should memorize this, but you really shouldn't, because this is a very special circumstance, right? It's a geometric series, it's a power series that follows a geometric progression, right? So e to the x, that's what this is. E to the x is a power series that follows a geometric progression, which means you use power series and a geometric series, right? You have to understand what these things are. You can't just memorize this. You really shouldn't. That'd be a really bad idea. You have to know what that is. You have to know what that is. You can't just memorize a formula and try and understand what's going on. So once again, this is your answer. I'm going to back up to... So if you want to take a screenshot, that's the whole problem. It's a lot of stuff. Calculus 2 is hard, so don't feel too bad if you're lost. But Calculus 2 is really rough. You have to do a lot of problems to understand this stuff, and it's really complicated. But I think it's fun. So just do series, do series problems. Do more integral problems and try to understand what's going on. So you can go ahead and take a screenshot of that, but this is the entire problem, basically. So if you have any questions, just send me a message or something.